Now let's look at parallel circuits and how resistors combine there. Now this is not as intuitive at first, but you'll see that it makes a whole lot of sense when you look at it in terms of this water analogy. So what I've got right here is a similar kind of comparison. I've got this plumbing system A. It's got my pump right here, and it's got one gravel-filled pipe here. I've got choice B, where I've got the same initial gravel-filled pipe right there, but what I've added to it is another gravel-filled pipe that is in parallel. And finally, for C, I've got these same two, this one, and I've added even another one that's even narrower, a greater resistance than those other two. So my question to you is, which one of these, A, B, or C, will have the most resistance to water flow? Now, there's a very, very common mistake that is typically made right here. And people think, oh, more resistors. Shouldn't it be more resistance if there's more resistors? In fact, the lowest resistance to flow in this case will be from C. So the most resistance is A. A has the most resistance. Now, why is that? What's going on? Why does this have the most resistance? Well, there's a lot of good analogies that you can use. One of them is, okay, if you have a pool, an above ground pool, and you punch a hole in it, water starts leaking out. If you create another opening, like punch another hole, will the water leak out slower or faster? It'll leak out twice as fast. There's twice as much space for it to get through. So that's one good analogy of why the more resistors you have in parallel, actually the less total resistance there is felt by the power supply, or the pump in this case. Another analogy is, let's say we have a bunch of seniors, okay, on, let's say, oh, I don't know, May 28th or something like that. We got a bunch of seniors that are all in here, and let's go ahead and draw them in there. Got a bunch of seniors all in here, and this is, they're trying to get out of school, and let's say this is the door to get out of the school. And the door is open, so these seniors start pouring out once the bell rings, but turns out that there's going to be a stampede, so a smart administrator opens up another door, like right here. So the seniors are pouring out there, smart administrator opens up another door. Wow, that relieves a lot of that, the senior congestion there. And another administrator, thinking very wisely, here's a bunch of seniors in here, opens up, so they got the first door and the second door open. The third administrator opens up just a little teeny doggy door. Now, even though it's a really tiny door, there's a couple seniors that can get out of there, and they're like, get me out of this school. So even opening a really tiny opening will still be overall less resistance because you're just making more space. This one has the most space to get out, so that's the lowest resistance. This one, that's got the least opening to get out, so that's actually the most resistance to that flow. Similarly, you might guess here, which of these has the most electrical resistance? A, B, or C? Well, by analogy, it's A. One thing you'll see immediately is that if this one, it's really got the fewest openings to get through, this one has the most electrical resistance, you know that this one right here and this one right here, they've got to have less resistance than 3 ohms. So we're going to have an equation for this that allows that to happen. So in parallel, R equivalent is less than the lowest individual R. So whatever the lowest resistance in parallel is, the equivalent resistance has to be less than that. So all these have to be less than 3. The more resistors you add in parallel, i.e. you're just adding more paths, the less that R equivalent is. So what do we know about R equivalent for these circuits right here? For circuit A, Well, because we assume that these wires right here have no resistance, the resistance felt by the battery is just 3 ohms. What do you know about B right here? Well, it's got to be less than 3 ohms. And what do we know about C? Well, you see, we got our 3 ohm resistor right here, so you may say, oh, it's got to be less than 3. That's true, but we know even more about that. We know that for C, this one right here, it's got to be less than what? It's got to be less than the resistance of B, our equivalent for circuit B. So it's got to be even less than whatever this resistance is, because I've opened up another path. The equation for resistors wired in parallel, our equivalent is this. It's 1 over R1 plus 1 over R2 plus 1 over R3 plus dot, dot, dot. And for those of you in AP, you'll know that, oh, that looks just like capacitors in series. But this is resistors in parallel. And I've had many students say, well, isn't that just the same as R1 plus R2 plus R3? It is not. And I urge you to do the math with simple, like, 2s and 3 ohm resistors so you can see that it is not the same. Let's go ahead and find our total for A, B, and C. So for A, well, that's going to be easy. Our total is simply, we've already figured that out, it's 3 ohms. Let's figure it out for B, though. For the resistance for B, which I'll symbolize like this, it's 1 over 3 ohms plus 1 over 4 ohms. And you can do this on your calculator, or you can get a common denominator. Common denominator for that is 12. It's 1 over, this is 4/12, multiplying top and bottom by 4. 4 over 12 ohms, plus this will be 3 over 12 ohms. I just multiplied the top and the bottom by 3. So this gives me 1 over 7/12 ohms, which is just 12 over 7, 1.71 ohms. And it's got to be less than 3, and sure enough, it is. Now, what can you predict about C? Before you do any calculations, you should be able to predict what that's going to be less than. Well, if you've done this and understand it, you know that it's going to be less than 1.7, and go ahead and figure out the resistance of that. So our equivalent of C is equal to 1 over 3 ohms plus 1 over 4 ohms plus 1 over 12 ohms. Doesn't matter what order, as long as I put them all in parallel there. Doesn't matter what order I add them up in. And common denominator is 12 again. So this is 1 over 4 over 12 ohms plus 3 over 12 ohms plus 1 over 12 ohms. And we add that up. That's 4, 7, 8. 12 over 8 is what we end up with. 12 over 8 ohms, which is 1.5 ohms. And that's got to make sense. It's got to be less than what we had before. And sure enough, it is less than what we had before. So this is going to be 1.5 ohms. The more resistors you add in parallel, the lower the overall resistance is.